Okay, well, thank you very much. Thanks to Todd Coleman for the invite. Unfortunately, he couldn't be here today. But it's always nice to be in the United States, and I've been to Champaign a couple of times. I've been to the Allergen Conference, and this is a nice part of the country, and I always enjoy coming down here. So, what we're talking about today, let me just give you some background to my general areas of research. So I did my PhD with Frank Shishang on the subject of LDPC codes, and my postdoctoral research was mostly in the area of wireless. And as I described my research program to people, those are the areas that really pay the bills, if you like. They're the areas in which I publish most of my papers and have most of my grant money. But I think there's always room to sort of explore beyond that and look at some unusual areas. I'm the kind of guy who really likes to sort of see where connections lead in other fields. So this is one of those fun projects that doesn't really pay the bills, like I say. So what we're going to talk a little bit about today is how to communicate with molecules among very tiny devices. So it's first appropriate to ask, how do tiny devices communicate? Well, what does a tiny device look like? Well, there's a device. That's not very tiny. Everybody knows what that is. You might know what that is. We've got a few of these in our lab. They're called iMotes. So there's a size of a US quarter for comparison. The biggest part about this package is actually this 3 AAA battery pack on the bottom. And in fact, the radio, there's 3 elements stacked here. Power, the radio and controller board, and this sensor board up here. The radio board is all that you really need to communicate, and that's here. Getting even smaller and smaller, many of you have probably seen that picture. This is a tiny, tiny, tiny little radio on this package here, complete with, there's a couple of rudimentary sensors on there and a solar panel. So, I mean, we in this room are most likely biased towards thinking about communication electromagnetically. So all of these sort of make sense to us. If we think, how do tiny devices communicate? The first place we're going to go is probably to electromagnetism, or at the very least, even if not to radio, then maybe to optical or something like that. So most of the information theory that we're accustomed to is electromagnetic. So, like I said, free space, EM wave propagation. If you want to talk about more traditional modes of communication, we can talk about wireline communication using voltages and currents, and even optical communication using photons. So these are all very electromagnetic ways of thinking about communication. So it's not at all obvious, in spite of the dramatic advances that there have been in lithography and device manufacturing and so far, it's not at all obvious that these kinds of techniques really scale down very well. So there's for instance, a natural energy and complexity cost to having a radio. You need things like modulators, demodulators, antennas. Remember, antenna efficiency is reduced the smaller the antenna gets. The antenna needs to be some proportion of the wavelength in order to be highly efficient. And furthermore, in a lot of the applications that we think about, radio frequency communication might not necessarily be appropriate. So, for instance, in the human body, now I'm aware that there exist devices within that go into the body and manage to communicate outside of it with electromagnetism. But really, what you're doing when you do that is you're sticking a radio inside a saltwater bath, and that has obvious energy penalties and efficiency penalties. On the other hand, it's appropriate to ask, how does nature solve this problem? So nature is composed of trillions and trillions of nanoscale machines that have evolved over billions of years, and they have evolved to solve the communications problem in interesting ways. In particular, these are nanoscale machines. They communicate by exchanging not electrical messages, but chemical messages. So bacteria and other cells, so the cells in your body, which are all related to each other in some way, and even independent bacteria communicate by exchanging chemical messages over a fluid medium. So the most common example among bacteria for this, among independent bacteria, is called quorum sensing. So what quorum sensing basically amounts to is this. You have a population of bacteria, and each one of them needs to know basically the local concentration of its species. Once the local concentration of a species gets above a certain threshold, the bacteria will change their behavior and do something different. So for example, a bacteria is floating along, suddenly it detects a colony of bacteria, so it will swim towards the colony and attach to it and start acting as a member of the colony rather than an independent organism. So this is a perfect example of communication. So what the bacteria are actually doing is they're releasing little chemical markers into the environment, and their neighbors are sensing them. They're sensing them and estimating the local population. What's more, if you want to talk not about independent devices, but about cells within your own body. Cells within your own body are constantly exchanging control messages, information messages, and so on, chemically amongst each other to regulate each other's activity. So if you look at the biological literature is absolutely chock full of stuff on chemical communication, on how biological systems communicate messages amongst each other using molecules that diffuse, or molecules that are driven, or molecules that are exchanged in some flow channel or something, or things of this nature. So there's just a ton of information out there. Until about 5 years ago, though, essentially no one had ever looked at this from an information theoretic perspective. So that's quite a remarkable disconnect. There's this huge volume of experimental literature and explanatory literature about using chemical markers, exchanging chemical markers to send messages. But the information theorists have completely ignored it. There's been absolutely no attention paid, probably because we've been so busy dealing with electrical communication that we didn't really need to do this until now. So, the thing about the biological literature, as I say here, the biological literature tends to explain but not exploit. In other words, what the biologists are trying to do is they're trying to figure out what the cells are saying to each other. And they're not asking the question, how can we take this and send the messages that we want to send? But what's known is that, or what's actually become interesting recently, there's this emerging field called systems biology. So what systems biology does is it takes, it's actually freaky Frankenstein-y stuff. So what systems biology does is it takes genetic components of existing bacteria and basically reassembles them at will to perform arbitrary tasks. So basically, what systems biology is all about is creating new life forms that do engineered things. So one thing that they've done, there's a group at Princeton led by a guy named Weiss, and what he's done is he's managed to take quorum sensing genes and put them together in ways that are under his control. So therefore he can create, if you like, transmitters and receivers in biology and chemistry. So a few, there are a number of engineering groups that have that are starting to take a look at this. The most recent sort of engineering paper, the earliest engineering paper that I'm aware of is by a guy named Satoshi Hayama. He's a researcher who splits his time between the University of Tokyo and NTT Docomo. And he wrote a very early paper on how to actually take these exploited biological systems and translate them into an engineered communication system. So there's two streams of research that are really going on here. One is sort of bottom up, if you like. So the bottom up research is let's take components that look like transmitters and receivers and try to send a bit between them. My research is more top down. I'm looking at this from the traditional perspective of information theory and communications theory, and I'm asking the question, what are these things capable of? How can we abstract them away and create useful channel models in the same sense of the adequate Gaussian noise channel, the minor symmetric channel, and so on.